In this lecture, we are going to learn a new method to solve beam deflection problems. And this method will make your life so easy to solve beam deflection problems. You will not want to use any of the other methods, for example, the second order method or the fourth order method or even the method of superposition. So this method, I personally like this method so much, I would maybe rather just go ahead and write it that to solve your beam deflection problems, this is an amazing method which makes your life extremely easy to solve deflections, slopes, and so on, given any type of beam, given any type of loading. So let's go ahead and take a look at this method. So that's the whole objective of today's lecture. And but first, why do we need to learn this? Why can't we be just happy with the second order method or the fourth order method or with the method of superpositions? Well, if you think about it, that do you actually need it? Do you actually need to know another method, which is the using the singularity functions over here? So now if you sort of think of the different techniques that we learn, for example, the second order, fourth order, or the method of superposition. Suppose, for example, say you have a beam, right? Suppose the beam has say simply supports and say a multitude or different variety of loadings. For example, let's say the beam has a point load somewhere, say it has a triangular load somewhere, maybe it has a point couple somewhere, maybe it has a uniformly distributed load at the very end over here. Okay? So suppose if you are given a beam like this, where at different points of the beam you're asked to find, say, the deflections or the slope and so on. Even if you do the second order method or the fourth order method, if you do either of these two methods, you see you have to have many different sections to write out your equations for the moments, and then you have to use the support conditions and the continuity conditions and so on. For example, in this problem we are looking at, we have to maybe take a section here, take a section here, 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 as well as here. So how many do we end up with? It is 1, 2, 3, 4, 5, and 6. So 6 different sections. So you will essentially have 6 times 2, so that is 12 constants of integration if you're doing with the second order method, right? And now to solve these constants of integration, you have only two boundary conditions. Remember, the only two boundary conditions are from the beam are y equals to 0 at x equals to 0 and y equals to 0 at x equals to L. So to solve the additional, you will need additional equations to solve all the constants of integration which you get from the continuity function. That is, at each of these sections you have the the continuity of the slope as well as the continuity of the deflection. So you see how difficult your life becomes. Now that sort of gives you a glimpse of, if you are using second order or fourth order method, what are the problems. Now you might argue that okay, you will use the method of superpositions, but see that for this kind of beam, how many different beams you have to break it up. So you have to break it up in a beam with a simply supported with a point load, a beam with a triangular load, a beam with a point moment, a beam with a UDL. You have to find the individual deltas or the individual slopes at whichever is their point of interest. Then you have to go and aggregate and have to add them all back together. So both of these techniques, or all these three techniques, the second order, fourth order, or the method of superposition, it makes your life too tedious. So that gives you the answer that do we need it? Yes, we need to know a method which will very efficiently solve your beam deflection problem and your beam slope problem. So before going ahead and solving problems on that, first we will have to learn what is a singularity function. And this method was actually discovered by the British mathematician William Henry Macaulay, and it is also known as the Macaulay's method of solving beam deflection problems. So let's go ahead and first take a look at some of the mathematical rules for the singularity functions and how we can apply them to solve the beam deflection problems. So now we will learn some of the mathematical rules of these singularity functions, and also which are known as the Macaulay functions after the British mathematician William Henry Macaulay. So we will particularly take a look at what are the different mathematical rules for these Macaulay functions. Now let's first define that how these functions look like, and then how they integrate and so on and so forth, right? So a singularity function is typically defined as, I will go ahead and write it. So a singularity function f of x, that is a function of x, is written as equal to maculae brackets. So these brackets are known as the maculae brackets. I will write that out as well. X minus a raised to n. Suppose you have a singularity function which looks like this, that within the maculae brackets. So these brackets, let me write that over here. These brackets are known as the maculae bracket. So if you have a singularity function defined by something like this over here, what does this expand to? So let's take a look at that. So if we have a singularity function x minus a within the bracular brackets raised to n, as long as your x is greater than a, this boils down to the simple function within the regular brackets that you have, x minus a exponent to the n over here. But when x is less than a, this becomes equals to 0. And let's also make a note that this entire thing is valid for values of n, this exponent n, which is greater than 0. So now that we have a function defined as this, let's maybe take a look at a couple of examples that how this function typically looks like. So the easiest way to understand this function is that as long as your x is less than a, you have a 0, and immediately when x becomes equal to or greater than a, this function triggers and then the function gets activated. So other than that, when x is less than a, it is a negligible, it's a 0 quantity, and immediately when you're hitting that a and beyond that, this function gets triggered up. So let's look at maybe a couple of examples for this one. For example, if I give you a mathematical a singularity function like this. So we are given this singularity function over here that f of x is 3 times within the maculae brackets x minus 1 raised to 0. And this is where I have just drawn the axis, where my x-axis, where my horizontal axis is x and my vertical axis is f of x, right? So if you take a look at this function, as long as your x is less than 1, for example in this region, if you draw the function, it is just going to come out and be a line like this over here, because before when x is less than 1, we have it at 0 over here. When x becomes equals to 1 directly, you are jumping over to this one over here. So then you are going to have 1 minus 1 when x equals to 1 raised to 0 within the regular brackets over here. So that means 3 times 1 minus 1 raised to 0. Anything raised to 0 is 1. So it is going to jump up to 3. Now you see beyond 1, when x becomes greater than 1, for example when x equals to 2, again this is still valid. So 2 minus 1 is 1, but it is always raised to 0, so that entire quantity becomes equals to 1. So essentially for any point x which is more than 1, the value of your singularity function or the maculae function stays constant at a 0 stays constant at 3 over here. So let's look at maybe another example. So if you see this particular function, a similar kind of a thing, as long as x is less than 1, you have a 0 over here. So for any value of x which is less than 1, it is going to come and be a 0 line. So here also my x-axis, horizontal axis is x and vertical axis is f of x over here. Now say when x is greater than 1, so let's say for example at x equals to 1, you have 1 minus 1, it falls back to this one, 1 minus 1 over 0 over here, and 0 times 2 is also 0, so this it stays at x equals to 1 as 0. Now when say x equals to 2, right, so when x equals to 2, then this function becomes over here 2 times, since 2 is greater than 1, so I am falling back to the regular parenthesis over here. So 2 times 2 minus 1 raised to 1 becomes equals to 2. So at x equals to 2 over here, my value of this function is also equals to 2, right? Now what happens when x equals to 3? Okay, so this one was x equals to 2. What happens when x equals to 3? When x equals to 3, then again I'm falling back over here because 3 is greater than 1. Remember, this a over here is 1 over here. So when x equals to 3, then this function reduces to 2 times 3 minus 1 raised to 1. So that is 2 times 2, so that is equals to 4. So when x equals to 3, the value of the Macaulay function is equals to 4 over here. So you see it's a sort of a linear increase that you have over here. So if you have to draw this function, it will look something like this over here, right? So these are the different tidbits of how the Macaulay functions or the singularity functions behave. So I hope you got the idea that as long as your point is before where you are having that particular value of a, right, that up to that particular point the value of the function is absolutely nil, and beyond that it kicks up. It can be a constant, it can be a linear line. If it was a if this was a square over, it will be quadratic or something like that, all right? So overall you get an idea of how the Macaulay functions behave and how they look like. Now there are certain integration rules for Macaulay functions which is going to be phenomenally helpful for you while you solve some of the beam deflection problems. So let's go and take a look at what are some of the integration rules for the Macaulay functions which are there. So I'm going to go ahead and scroll down and write it out. So the integration rules for Macaulay functions are as follows. So if you take a Macaulay function, something of the order of like this, and if you try to integrate that, let's see how that looks like. These two are the integration rules. So if you see the first integration rule, see, remember this one is not within the regular parenthesis, it's within the Macaulay brackets because we are looking at the integration rules for the Macaulay function. So if you have a function like this, as long as your n, this exponent n, is greater than or equal to 0, it follows the integration rules for the regular functions. For example, if you had within the regular parenthesis as well, the integration rule will be as simple as that, because your exponent is becoming n plus 1 and in the denominator you are having to add another n plus 1 over here, right? Now there should also be a constants of integration. I have not written that just for simplicity. When we will solve beam deflection problems, you can add that over there. And also you see that the other rule is that when n is less than 0, then it falls back to this one. You still have the exponent which goes from n to n plus 1, but now you have nothing in the denominator over here. So these are the rules of integration for the Macaulay functions which are there, right? So I hope this overall it is clear to you. So you just have to have it in your mind that how the Macaulay functions look like and what is the integration rule of the Macaulay function. Actually you don't even have to remember that much. As long as you understand, that's fine, because typically you use some of the charts or the Macaulay charts for solving beam deflection problems, which we will take a look. But I hope you could appreciate that how it takes care of these discontinuities, that before that discontinuity you have a 0 and then you have either a constant or a or a linear or a quadratic expression like that. And also the two different integration rules, that as long as your exponent is greater than equals to 0, it falls back to the regular integration. Now remember, even when you are doing regular integration, it is still within the Macaulay brackets over here. You have not gone back to the regular parenthesis. So now from this one, depending upon your x, whether it is greater than a or less than a, you will have an expression for this guy over here. And the second rule is that when n, that is this exponent, is less than 0, in that case you just have the exponent go from n to go up to n plus 1, but there is nothing in the denominator over there, right? So now what we are going to do, that for our different loading cases, for example, if you think about loads in beams, either you can have mostly 4 types of load. One of them is, say, a point moment somewhere. You can have a point load, which is the very common. You can have a uniformly distributed load, or you can have a linearly increasing load. So now let's see that using, for these kinds of loading conditions, how do the maculae functions and what is the interrelationship of the maculae functions that emerges, which will help you greatly to solve the beam deflection problems in one single go. You will be using maculae functions, you can write the expression for the moment for the whole beam in just one single go. So let's first go ahead and take a look at the interrelationships between the different kinds of loadings using the maculae functions before going on to some of the problem example. Now we will look at the interrelationships between the different types of load using the singularity functions that is there. So as you see over here, what I have reproduced on the left hand side over here is what we just saw, that what are the maculae functions or the singularity functions, and these are the integration rules for the singularity functions which we have seen. And what you see in this chart, which we are going to fill it up soon, is that what are the different types of loadings that you have over here. For example, you can have a point moment, you can have a point load, you can have a distributed load, you can have a triangular load, and so on. And also please note one thing, that all of these are getting activated within the beam beyond a certain point, which is quite realistic, because if you take a look at a beam, you can have a certain place in the beam where you have the point load or the point moment, or a triangular loading starts, or a uniformly distributed loading starts, right? Or you can have the uniformly distributed load throughout also, in which case your this A becomes equals to 0. Okay, so now one very important thing which you must make a note of to properly use the maculae functions is that your load, so let me activate my pen over here, that your load P and W is considered positive upwards. So this load P is positive upwards, this W is considered as positive upwards over here, and M, the moment, is considered positive clockwise. So these are very important things to note. Otherwise, when you start to use maculae functions for your beams, you have to keep a track of many different signs. Once you remember this particular convention, it becomes very easy for you, and you can easily remember from this figure over here that, say, in the exams or during solving the problems, you will be making use, you can make use of these charts which we are going to look at. What are these numbers which are going to come over here, what are the expressions that you are going to come over here. You should just keep in mind that all the things that you are seeing here are positive. So moment is positive, so that means your convention is clockwise, moment is positive, P is vertically up, so convention for positive P is acting when it is acting vertically up. Convention for loading being positive is that when it is acting vertically up, and also for this triangular load over here. Okay, so now let's start with the first one. The first one is the moment that you have over here. So you see that in each of these columns you have the loading function, that is the W, the shear function, which is integral of W of X. This we have seen before, but remember when we had seen in the BMD SFD chapter, it was V equals to minus W of X, but in that case the W was acting vertically down. Here the W is vertically up, so it automatically becomes a positive sign, and the moment M is integral of V dx. So these relationships we know already from our discussions on BMD SFD. Okay, so let's first start with this guy over here. So you see here in this beam at a distance A, you have a moment M naught over here which is acting clockwise, that is positive. So within the beam, what is the point at which the moment is getting activated? If you think of activation like the singularity function, like something like this over here, right, it gets activated only when X is greater than or equal to A. So before that it is 0. So let us write the singularity function for the expression for the moment. So that is going to be equal to, so your M will be equal to M naught times X minus A within the maculae brackets raised to 0, right? So does that make sense? Yes, it does, because as long as X is less than A, you do not have any point moment over here. So in that case, M becomes equals to 0, and this gets activated only when X equals to A. So when X equals to A over here, you get, and A, when X is beyond that A also, that your moment function is getting activated within the beam. So now if this is the expression for the moment, that is obtained by integrating the shear. So now you have to go back to the integration rules over here. Since it is obtained by integrating the shear, so if you see, if it's a 0 over here, so it must be following this one, because for n less than 0, so this expression must be m naught x minus a raised to minus 1, because when you integrate that one, when n is less than 0, then you get n plus 1, that is minus 1 plus 1 becomes equals to 0. So that is exactly what it is over here. So this expression for the shear is m naught x minus a raised to minus 1. Now we know the shear is an integration of the load over here. So now since this is minus 1, it again falls back to this one. Integrating what expression will, so the question you should be asking that what do I have to integrate to get the value of the shear as like this. So the value, so the expression for your W must be m naught x minus a raised to minus 2, which you see this is over here. So I hope it is clear that for one particular loading, all we are doing is that as soon as I'm hitting that spot where the loading comes, I'm activating my function, and once I've activated that, I am just finding the interrelationship between the load W, between the shear V, and so on. Okay, so let's go to the next one over here. You see at this, for this beam, P is, imparts, if you remember our discussions on BMD SFD, this is the place where this load P activates a high amount of shear. So P is essentially related to the shear force that you have over here. So again, similar to what we did before, here where in the beam is the P getting activated? Yes, it is getting activated beyond A. So the value of the shear, the expression for the shear in this case is going to be that your V is equals to P within the maculae brackets x minus a raised to 0 over here, right? Now, so this gets activated at x equals to a and beyond that, but before that it is equals to 0. Now, if we use this one over here, and how do we get the moment? The moment is an integral of this one, so this boils down to this one over here. So it is going to be P times x minus a, 0 plus 1, that is equals to 1, divided by 0 plus 1, that is equals to 1. So it should be P times x minus a raised to 1, and that's exactly, oops, sorry, I wrote the previous one before, so let me activate this one and then take you back to the previous one. So this is what we deciphered, P times x minus a raised to 1. Now if you want to find the loading function here, so you have to again ask the question, integrating what will give you this one over here. Since this is 0, it boils down to what we did previously, so this must be px minus a raised to 1, and it falls back to this integration rule over here. Now let's go on to the third one. So for the third one, we are going to write the loading function here directly. Here also the loading function gets activated only at a and beyond, and not before that. So here the expression for W would become, W will be equal to W naught, and within the maculae brackets you have x minus a raised to 0 over here. Now once you have this, now you know that you have to follow this integration rule. So for the first one, you will have this guy over here, that your shear is W naught x minus a raised to 1, and for the second one, this you will have the denominator as well, so it will be 1 plus 1 raised to 2, x W naught x minus a raised to 2 within the maculae bracket, of course, divided by 2 over here. So I hope you understood the first three, and let's take a look at the last one. So last one is also a pretty convenient expression where you have to deal with beams with triangular loading. So for this case, let me go ahead and write the expression for W. So in this case, you will have W as, remember, this is a triangular load with a slope m over here. It starts with 0 and linearly increases with the slope m. So W is going to be equals to m times x minus a within the maculae brackets raised to 1. So this is the expression for W for this kind of loading that is there. As you see at exactly here, it is 0 and it slowly linearly increases with the slope m over here. Now to get the shear and the moment, same, you just have to integrate that one. So we keep on integrating and you get the expression for the shear as something like this. You have divided by 2 because you have the 1 over here, you are using this rule of integration, so 1 plus 1 equals to 2, and correspondingly the moment comes at something like this over here, right? So this is the overall chart which we are going to use to solve our problems using the maculae functions. And you will see that once you have all these relationships over there, it becomes very easy. So essentially, after learning all of these different interrelationships, how are we going to use them? Well, the way to use them is that now you know that within a beam, if you have a uniformly distributed load W or a triangular load, you know what is the corresponding expression for the moment that is there for uniformly distributed, or even for this one, even for here. For a load P, you know that what is the corresponding expression, corresponding singularity function or maculae function expression for the moment. So essentially, so see, the advantage of this is that now if you are given a beam with point load, triangular load, uniformly distributed load, point moment, you can express each of these in terms of the moment, because you know the interrelationships between these loads and the corresponding moment using the singularity functions. Now, the advantage to that is that once you have expressed everything in terms of the moment, you know your general expression that your d square y by dx square, ei d square y by dx square equals to the moment of x, right? So now if you can write one single expression for ei d square y by dx square in terms of all the converted moments, all the loads, all the point loads, udls, triangulars converted to an equivalent moment using singularity functions. You can convert everything to that, and then you can go ahead and solve that over here. So let's go ahead and take a look at a couple of problem examples and see that how can we use singularity functions to solve beam deflection problems very quickly.